NVIDIA GPU node is. So we can execute this NVIDIA.-smi command. And what we'll do is it will print out what GPU card we have on this cloud node. So here we have Tesla T for a GPU card. Okay, so sounds good. Let's go ahead and execute that remaining last command, right? So here we want to just look at the example of how it would look like to launch a pre-trained, quick pre-training job. So I'll copy this command and I'll shift right click and paste as a plain text. So you can, okay, so you can execute this command or you can type it manually as well. Before executing that command, I just wanted to mention very briefly that if you want to follow how the training process is going, you can also configure an account with the weights and biases. So there's uh, a website that you can go and create an account, and the you can basically generate your account's API key that you can pass in this pre-training workflow, and then you can follow in real time, for example, how the training job is proceeding, right? So if you have time or if you already have the weights and biases key, you can go ahead and use it when you are asked to submit that key. But for now, we just will execute this pre-training command. And like I was mentioning, it will ask you for weights and biases key. So if you have existing account or if you have created or if you want to create an account, you can follow these options. But for now, I'll just skip this step. So I'll enter 3 and just to select don't visualize my results at this point. So once you enter, uh, it will basically ignore the weights and biases setup and it will start the pre-training, model pre-training process. So very quickly, what's happening in model pre-training process is we have certain data sets. So let me, so before I go to show what what we are providing as an input, okay, I think the prompt is going too fast. But yeah, basically, if you have your weights and biases set up, you can follow the progress there. Otherwise, what this pre-training script is doing is basically taking a data set that you have specified in your pre-training script, and it's 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 starting a training process. So basically, it will divide the data set in chunks uh, in a specified size of chunks of smiles, and then it will take those and it will start training process. And sort of this training will happen in epochs. So epoch meaning the model has seen all the example ones that are there in the training set, and then it will do the validation. So you can specify what you want to have. So what's the epoch size, what's the validation data set size, what's the input data set you are providing, and all the details like that. And you can follow the GitHub page to find more about what parameters you may want to tweak. And in the prompt, it will print out all the details, right, where it's at the training and what step it is. So for now, since we are not going through the whole training process, and anyway, we don't have a very powerful node here that would go through all the training steps, I'll just terminate this training process by pressing Control C. And once you press Control C, it will stop the training. So you'll see some training statistics printed at the end. Okay, and I also wanted to show what we have in the training database. So very briefly, I'll just uh, uh, go to the data where we have training data. Just a second. Yeah. So we have a subset of Zinc dataset as a training data, and we have already sort of provided training, validation, and test sets. So that you added the data set in 3 parts. You can read more about what we have here and in the overview. Uh, so in the original model pre-training, we use about 1.45 billion small molecules in a SMILES format. For this particular example, we are using 100,000 compounds, a very small set. So it's a subset of Zinc 15 dataset. We are providing 100,000 compounds in training, 5,000 compounds in test, and 5,000 in validation dataset. And they all are in the, so if you go to the train, they are all in the CSV format. So if I say head X, so you'll see it's a comma separated format, CSV format. It has a Zinc ID and its corresponding smiles string. So at this point, we will exit out of this shell. So you can press Control D or you can manually close it clicking on the cross sign. Okay, so that sort of concludes our first step of going through or like taking a sneak peek at model training or pre-training, or if you have a custom data set, you can use it for retraining the megamolbart model. I'll pause for a second and see if there are any technical issues going through this. Of course, you can also follow these steps later on once the lab is uh, concluded at your own pace if this speed is too fast. But yeah, please keep posting your questions if something is unclear. Okay, so looks like everything is good. Let me adjust my screen and let's move to the step 2. And this step basically captures the capability of pre-trained model, right? So we have a pre-trained model that was trained on 1.45 billion smiles from Zinc dataset. So it has all that sort of chemical space, sort of, it has captured that chemical space relationships among those tokens that we use in the training. Now let's see how we can use this uh, pre-trained model for generative chemistry and for predictive modeling. So here is again the content outline for this second step. So there are 3 main sort of tasks that we want to visit. First one is to just go through the inference functions. So what this model comes with. So it comes with the inference wrapper, and through this wrapper, we can access some of the functionalities from this model. So we can go from smiles representation to hidden state representation. We can go from smiles to embeddings, and we can also obtain hidden state smiles from hidden state. So basically traversing to the latent space and traversing from latent space to chemical representation. I'll show or I'll talk more in detail about what these steps mean. In the second step, we'll use one of the functionalities to explore chemical space. So basically generate new compounds, uh, which is similar to our query compound, right? And finally, we will obtain the embeddings for a data set, chemical data set, and we'll use it for predictive modeling. Okay. All right. So if you have any questions, please feel free to post them in the chat. Okay, so let's jump into the specific tasks. So for those who are not familiar with the Jupyter Notebook, this sort of interactive programming interface. You can execute the commands that are there in individual cells by simultaneously pressing Shift Enter. So like I just press Shift Enter when I clicked on the first cell. So what it does, it executes all the commands that are there in that particular cell. So in the first step, what we'll do is we'll import some of the essential libraries or modules. Some of them are from QML, QDF. So these are Rapids libraries that are accelerated uh, that are accelerated using GPUs. So basically, you can take advantage of GPU acceleration. So these are analogous to Pandas or NumPy that you use. So please check out Rapids as well. And we'll also import functions or libraries from RDKit. So RDKit is widely used open source chemoinformatic package. And I'm providing all the links here, so you can follow those links later on to learn more about these packages. Okay, so coming to the inference functionalities, right? So like I mentioned, this pre-trained MegaMolBART has several functionalities for inference, and you can access these using inference wrapper. So in this cell, we will make connection with the inference wrapper, and we will take a couple of smiles uh, just to explore these functionalities, right? So in this example, we'll be taking smiles for two antimalarial drugs, mefloquine and hydroxychloroquine. You can take any other smiles, but these are just the two representative smiles. And if you execute this cell, you'll see how these two input components look like. So we are just making a connection to the inference wrapper. We are taking two example smiles and we are visualizing them, how these two compounds look. Uh, Again, we will use smiles format to interact with the inference wrapper, but the 2D representation is just for us to see how these compounds look like in 2D. Okay, all right, so moving on, let's first explore the first capability, right? So we have smiles. This is just an example. We have smiles and we want to obtain hidden states. So what hidden state captures is basically a representation uh, which is obtained from pre-trained or learned model. And what we are basically getting is we are providing a smiles. It passes through encoder and it provides a hidden state representation. So it's a matrix, a float. And let's see, uh, by executing this cell, what we obtain. So it obtains these two parameters, right? Hidden state and pad mass. And if we look at the shape, you'll see that the hidden state has, so since we are providing two compounds, it provides a PyTorch tensor object. So basically it has these dimensions. So it has 46 and 512. So this sort of size of those two tensors that we obtain. Okay, so that was obtaining the hidden state, right? But there is another representation that you can obtain from hidden state. So that's sort of next uh, type. So if you uh, execute this cell, basically it will obtain embeddings. So it's again similar going from original smiles through encoder and to the learned representation chemical space and obtaining embedding for the chemicals. And here if you look at size 512, again we are obtaining two such tensors for two compounds, but you will see there is a collapse of this matrix into a single dimension. So basically what we are doing is we are taking the hidden step and averaging all the values for all the 46 sort of